Okay, next is conservative versus non-conservative forces, and I did had a playlist, I mean a video right before this one on my playlist. So hopefully you now understand what conservative versus non-conservative is. On your notebook you can take a note of examples here, but I did explain it on the previously, so I'm gonna skip this part and move on to the this kind of an example, but we're not solving it, we're just kind of examining it. Okay, so we are considering a sliding object across a frictional surface, and by giving it an initial velocity. But again, how we give that initial velocity is not a question that we focus on. There was a force, probably an applied force, maybe we did it, like we pushed it, and but then we are no longer holding the object, so the force is no longer there, but we gave it an initial velocity. Okay, so the thing is, initially the object has a velocity, and after a while it just stops. Okay, so what happened? How did the energy transfer, and from what type and to what other type? Okay, so we're investigating this. Because if it was frictionless, what you would guess is, right, it would just go forever with that speed. So then let's just kind of think about the free body diagram. There's a weight force downward, normal force upward, and since the object moves to the right, intended motion is to the right, then there's going to be a friction to the left, and it is kinetic because the object is moving relative to the ground. So we have Fk for that. And there are no other forces on it again. Now let's think about the energy and kind of think about the pieces in the energy conservation. Since we have a free body diagram, if you think about the work done, since the displacement is to the right, as you can see it with this vector, and the weight force and the normal force are perpendicular to the displacement or to the motion, that would make the cosine function in the weight, in the work definition, right? It is f d cosine theta. When you open up that dot product, that theta is 90 degrees. That means the work done by normal force and the weight force are both 0, so they do not do work. And we are going to talk about the friction later, but let's also talk about the potential energy next. So for this one, now we got to kind of pause and think about it. There are two types, right? There could be a gravitational potential energy change, and that would be non-zero if there was a change in elevation. This happens in horizontal, so there's no change in elevation. That means the gravitational potential energy change is 0. And next, there's elastic potential. So we need to think if that is changing. That would only change if you have a spring-like object and there's a stretch and compress. And we do not have a spring-like object in this problem. That means there's no change in elastic potential either. So all the potential energy changes are 0. And next, let's think about the kinetic energy. So initially, we have kinetic energy. It's shown as 1/2 mv squared, and then it goes down to 0. Okay, so it starts high but drops to 0. So the question is then, where did this go, the energy go? Because we see that there's no change in energy, potential energy. Normal force and weight force are not doing work. Then we gotta look into the piece that we skipped, right? The friction force. So hopefully we understand these two. So what happens then is friction force converts the kinetic energy to internal energy. Okay, so friction force is again not a conservative force. So it is not associated with a potential energy. Okay, but it is going to be associated with internal energy. Why is that? Because it is going to warm up. So when you drag an object on the floor, as we see it in this example, the surface between the object and the ground will warm up. Okay, so there's going to be some heat, some temperature rise. And if you remember, the internal energy so far we said it is 0 because there was no temperature or pressure change. So if you change one of those, then you will have that. And that means the kinetic is converted to internal energy, and it will there will be heat or heat released or something. So we cannot convert that internal energy back to kinetic energy. Okay, that's why it's non-conservative force, and you cannot get it back to the system. But of course, energy is still conserved, because when we write the energy conservation, we have all those terms. We just say that, okay, kinetic energy turns into internal energy. That's how we conserve it. Okay, so yeah, the heating the block, so if you look at here, heating the block up will not make it move. But if you think about a ball thrown up, it won't hit the ground at its launch speed either. If we have like things like this, and drag force, if you're losing some energy to friction or drag or air resistance and things like that. So things are gonna get more realistic with these assumptions. Okay, we've been making really simple assumptions. Now we're gonna make a little bit more accurate or realistic assumptions. Okay, so next is calculating potential energy. The thing that I've been saying, and like the key points, like you cannot have both potential energy and the work done by weight force, for example. So we are kind of going to see this, and I'm going to try to be quick on explaining this. So ball is shot upward. Okay, so we're looking at the figure with some velocity v. The only force acting on the ball is the weight force, and we are neglecting the drag force here. The work done by the weight force, if you look at here now, is going to be in the form of, since weight force is a constant force, it's W dotted with D, and that becomes WD cosine theta. What is W? It is mg, and D is the difference between initial and final, right? But it's always final minus initial. That's the displacement, and the angle between the weight force and the displacement is 180, so you're also adding that, and that gives you -1, and what you're getting is negative mg y final minus y initial. Okay, so that's the work done by the weight force. It's doing a negative work on the system, on the object, and it is negative, but potential energy goes up, right? When you're throwing the ball up, it reaches a higher elevation. That means it has more potential to do something useful, right? That's how we defined it. So when the work term goes negative, the potential is positive, and again, it's because those two terms are on the two different sides of the energy conservation. Okay, so if we now recall the energy conservation, we neglected the potential term because we are keeping the work done by the weight force in the work term here. Okay, you need to do one or the other. You cannot do both of them. So, and we're gonna kind of show why we need to do this soon. We are going to define the gravitational potential energy using this term. And next, we are saying that, okay, let's keep the work done by the weight force separate from the other one. So we're splitting out the work term due to the weight force separate. So this is the work done by the weight force, and this is the rest of the forces. If we have more forces, then they will do work maybe, and if they do, this is where they go. Okay, it's going to be here. So we just split up the work done. And then again, we are going to put this work done by the weight force on the left side. It becomes negative, as you can see in this line. So when you write this down, so there's a negative sign in the front, but if you remember, we already got a negative sign for that work done as well, so we are putting those together. That becomes positive. Okay, and when you distribute it, you get mgy final and minus mgy initial. I'm just focusing on this portion here. Okay, so, and we are saying that, okay, I already included the work done by the weight force, and I separated from the other ones. So next we are going to drop the subscript rest, and you got to remember that it does not include the work done by weight force because you put it on the left side already. So this is how we define the gravitational potential. We define it as mgy, right? We already done that. And what we are saying here is mgy final minus mgy initial is simply u final minus u initial. What is u final minus u initial? It is the change in potential. So we are saying that this is ug final and ug initial, so this is going to be delta ug, and g means the gravitational potential energy. Okay, so that's why now when you put it on the left side as the potential energy, you do not have it, the weight term here does not include the work done by the weight force. Okay, if you're keeping delta ug on the left side, do not include work done by weight force in total work. It doesn't mean that work done by the weight force is zero, okay? And if you have a change in elevation, it is not zero. But when you put it in this equation, you should not double count it because you kept it as delta UG. And you started from WW, right? And then you get to that. So this is, I think, hopefully it's nicely showing they are the same thing, but they're opposite signs because one is on the right side, the other is on the left, and hopefully it makes sense now. Same thing applies to elastic potential energy. So now we are looking at the horizontal spring case. Again, there's a compressed initial to final, and frictionless surface. And here's the free body diagram. We have the weight force and the normal force and the spring force. This is the spring force. Again, we use this lowercase f for the friction, and it is lowercase fs. That's the static friction. Please use differently than the spring force. Make a difference between friction and spring force. And what we do in this book is we keep the spring force as capital F, okay? So for that way you don't confuse, and if you look at the equation sheet, if it is little f, it is friction. If it is capital F, it is the spring force, if there's a subscript like s in there. Okay, so we did discuss this earlier when we talked about variable forces in chapter 7, and we got this, the work done was 1/2 kx initial square minus 1/2 kx final square. So it was initial minus final for the work term. Again, when you consider the energy conservation, now we're keeping the gravitational potential in, but that's the only potential energy, and we are keeping the work term for the spring force separate than the others, but we are keeping it on the right side. Okay, and as we did this before for the gravitational force, we are putting this on the other side, so we have that term right here. Next, what we are going to see is that term is really the positive of change in elastic potential. This is how we're going to define it. So this is the definition. When there are 3 lines, that means that's how it's defined. Okay, it's negative of that. So since the work done by spring force was initial minus final, and there's a negative sign in the front, if you rearrange them, change in potential, elastic potential energy is final minus initial, since you know that this is a change, and change is always final minus initial, right? So you have to do that. So, and that's what we have here, and that's for the potential energy. Okay, and again, the this work done ignores work done by the spring force. Okay, because it is now accounted in the change in elastic potential. It's really important, and this is a bit tricky, so hopefully now we kind of see it. Next thing, I want to quickly go over this before the example. So energy conservation, and we've been really applying this anyhow, so we are kind of looking at this in more detail now, but so we say that like we need to conserve energy. So I'm kind of reading here. Does this make sense? Why should we worry? Isn't energy conserved as a fundamental? So energy is always conserved, okay? And this is the reason. But this really tells you you may maybe you're giving in velocity or something in the system, so you have kinetic energy, but maybe that will be released as heat. So that heat goes away, but since energy is still conserved, right? So you may not be able to reverse it back to something useful. That's why you should not waste the energy, right? But in general, energy is conserved because of this reasoning. So work is the W is the work due to all forces. If you're keeping these two terms here, potential energy terms, it's going to be except the weight force and the spring force. Okay, if you have those forces, ignore them in the work term on the right side, because assuming you're keeping delta UG and delta UE. And K is 1/2 mv squared. That's the kinetic energy. It changes with the speed. UG is the gravitational potential energy. It changes with the elevation y. It's mgy. And UE is the elastic potential energy, and it changes with the compress or stretch. You need to have a spring like material to have this. So it's 1/2 kx squared. It is very important, and we do start with this equation. Now we split up the potential energy into two forms. Later on we will split up more and we will see more specific equation. So far we've been saying that this was simply delta U, right? And that's what you will use in the exam, but now we are seeing a little bit more details. And again, to determine the work done, you do draw a free body diagram, but although you show the weight force and the spring force, although they might do work, you will ignore them when you put it in the work done by those, you will ignore those when you put it back in the energy conservation, as long as you're keeping those delta U's, okay? Or you can do the other way around. You can ignore delta U's and then keep it as the work done by those forces on the right side. Okay, so next we are going to solve some problems.